In section 7.1, our goal is to use integration to evaluate area between two curves. Previously, we found area under a curve for just one function. For example, let's say I have a function, I'm going to call it f of x, a function with respect to x. And from a to b, I want to find the area bound by the function and the x-axis from this x value to this x value. Let's section off what that region looks like. So from A to B, I want this area that I'm shading in blue. Well, we remember that area means integral, so I would take the integral from A to B, this x-coordinate to this x-coordinate, of the function f of x with respect to x. Well, what if I have a function, call it g of x, and I want to find that area from A to B between the function and the x-axis. So that's going to be this shaded region in here. Well, similarly, I'm going to do the integral from A to B, but of g of x with respect to x. What if I said I want the area between those two curves? So that's going to look like this area right here. So I want the blue area, but not the part that is in the green region. When I say, but not this part, that means I need to take it away. I want all of that blue area, but not the part that is in the green region. So take it away. The bigger area minus the smaller area. And the shortcut way to write that would be with one integral. Combine them. The integral from a to b of f of x minus g of x. And there you go. And that's what we do to find the area between two curves. Now, how do I know which one is supposed to go first? Well, of course, when we're subtracting for area, we always want the big one minus the small one. So if these are functions of x, that means they're either going to be high or low. So I'm going to pick the bigger y. This is the bigger y values, the y values that are on the top, and these are the smaller y values, and I always want to subtract bigger minus smaller when I'm talking about area. So we can think of this as doing the integral of the function that's on top minus the function that's on the bottom, because then I'm always doing bigger minus smaller, and that's when it's with respect to x. So to cut to the chase, we remember that area means integral, and when we want the area between two curves, if they are functions of x, we do the integral of the top function minus the bottom function when it's with respect to x. Now I say when it's with respect to x because it's not always with respect to x. Sometimes we deal with functions that are functions of y. For example, let's say I have a parabola that is a function of y. I'm going to call that f of y, and another function, maybe I call that another function of y, g of y. If I want to find the area bound between these two curves right here, I have to think of that a little bit differently. So this is my x-axis and this is my y-axis, and when it's a function of y, I have to think of going in the other direction. The functions of y we think of as moving to the right or to the left. So when I think of which one is the big one here, I have to think of, well, how far to the right it is. And the numbers that are farther to the right are the bigger numbers. For example, this might be 2 and this might be 12. So I would do, if it's a function of y, the integral of f of y minus g of y with respect to y, or the integral of the function on the right minus the function on the left when it's with respect to y. So back to our notes, when it's a function with respect to y, f of y and g of y, we want to think of the integral of right minus left. That's when it's with respect to y. So to find the area of a region, it's good to first have a sketch of the graphs. Then we can determine if they're with respect to x or with respect to y, find the limits so we know how to bound our integral. Sometimes we need to find the intersections, maybe with a calculator, so make sure we know how to do that. Setting up the integral, either top minus bottom or right minus left, depending on what it's with respect to, those functions, and then integrate and evaluate the integral. So let's take a look at some examples. First, find the area. So I think again, area means integral of the region bounded by y equals 2 minus x squared and y equals negative x. Now without a calculator, because we have to know how to graph these without a calculator. So let's begin. We know this one is a parabola opening down and shifted up 2 units. So the vertex up here, parabola with a normal coefficient of 1, but opening down. So over 1, 1 squared is 1. Over 1, 1 squared is 1. Over 2, 2 squared is 4. Now, if you don't feel confident in graphing anything, whether it's a parabola or whatever, you can always pick points, plug them in, and plot the points that you evaluate. Y equals negative x, linear. Slope is negative 1 and starts at 0. 0, 0. So down 1 over 1. And the more precise you can be with plotting the points, the easier it'll be when we find out where the region is bound. Now, where is the region that's bound between the two curves? Bounded by those two curves. So touching both curves could be this region, but notice that there's no limit to how far I shade. I want the region that's completely enclosed and touching both of those curves. There's the region. Now both of these are functions of x. See how this has y by itself and it's with respect to x? That's how we know it's a function of x. The y is by itself and x is on the other side. So I know that I'm going to be thinking I probably want top minus bottom. So let's look at the whole region and figure out if I color in, the top is the blue, the bottom is the green. Over here, if I color it in from top to bottom, it still goes blue down to green. Over here, it still goes blue down to green. So always, if I'm doing a function of x, I'm thinking top minus bottom, the integral of top minus bottom. The function that's on top, the blue function, 2 minus x squared. The function that's on the bottom, the linear one, negative x. So I'm going to subtract these. Now I need to figure out where the region starts and stops. So if it's a function of x, I want these to be what x equals. These have to be what x equals. So where does it begin? At negative 1 on the x, and where does it end? At 2 on the x. So negative 1 to 2. Now, we can simplify a little bit if we want to, negative 1 to 2, and take away the parentheses, 2 minus x squared plus x with respect to x, however we feel like it to help us. We evaluate the integral and get 4.5. The main thing today is setting up the integrals. However we choose to integrate after that, that's up to us later. Let's take a look at another one. Find the area. Area means integral of the region bounded by the curves y equals x squared minus 2 and y equals 2. So again, let's know how to graph it without a calculator. Parabola opening up, shifted down 2 units. So normal size parabola, I'm going to plot those points. And straight line, y equals 2. Here's y equals 2. Easy horizontal line. Now I shade the part that's bound by the two graphs, and that's helpful to shade so I keep my eyes focused on the region. Now I'm going to determine top minus bottom. So here's the function on top, and shading down to the bottom, there's the function on the bottom. So this time the green one's on top. Everywhere I shade from top to bottom. Now, why am I picking a variety of places to shade? It helps me determine that these are in fact functions of x. It's a little bit easier to tell that the top is always on top and the bottom is always on the bottom when I shade in a variety of places. So I'm going to remember this integral has to be top minus bottom. And it's with respect to x. Y is by itself and x is on the other side. Y is by itself. There's no x's over here because it's just 0 x's, but we can still think about it's a function of x because y is by itself. Y is like f of x. Now I'm going to plug in what I have. This time the top one is the green one, so that's 2 minus the bottom one is the parabola, x squared minus 2 and with respect to x. Now I figure out where does it start and stop. Here the region starts at -2 and the region ends at +2. -2 to 2, and I evaluate my integral and I call it a day.